last minutes about the fast Fourier transform. Here's the idea. F6, our 6 by 6 matrix, there's a neat connection to F3, half as big. There's a connection of F8 to F4. There's a connection of F64 to F32. Shall I write down what that connection is? What's the connection of F64 to F32? So F64 is a 64 by 64 matrix whose W is the 64th root of 1. So it's 1/64th of the way around in F64. And F32 is a 32 by 32 matrix. Remember, they're different sizes. And the W in that 32 by 32 matrix is the 32nd root of 1, which is twice as far. See that key point? That's how 32 and 64 are connected in the W's. The W for 64 is 1/64th of the way. So all I'm saying is that if I square the W64, that's what I'm using for the 1 over W60. This is Wn is e to the I 2 pi over n. So W64 is 1/64th of the way around it. When I square that, what do I get but W32? Right? If I square this matrix, I double the angle. If I square this number, I double the angle. I get the W32. So somehow there's a little hope here to connect F64 with F32. And here's the connection. Okay. Let me go back. I'll do it here. Here's the connection. F64, the 64 by 64 Fourier matrix, is connected to 2 copies of F32. Let me leave a little space for the connection. So this is 64 by 64. Here's a matrix of that same size because it's got 2 copies of F32 and 2 zero matrices. Those zero matrices are the key. Because when I multiply by this matrix, just as it is, regular multiplication, I would need 64. I would have 64 squared little multiplications to do. But this matrix is half zero. Well, of course, the two aren't equal. I'm going to put an equal sign, but there has to be some fix-up factors, one there and one there, to make it true. The beauty is that these fix-up factors will be really almost all zeros. So that as soon as we get this formula right, we've got a great idea for how to get from the 64 squared calculations. So this originally we have 64 squared calculations from there, but this one will give us, we don't need that many. We only need 2 times 32 squared, because we've got that twice, and plus the fix-up. So I have to tell you what's in this fix-up matrix. The one on the right is actually a permutation matrix, a very simple odds and evens permutation matrix. The ones show up. I haven't put enough ones. I really need 32 of these guys at double space. And then you see it's a permutation matrix. What it does, shall I call it P for permutation matrix? So what that P does when it multiplies a vector, it takes the even numbered components first, and then the odds. You see this one skipping every time is going to pick out x0, x2, x4, x6, and then below that it will pick out x1, x3, x5. And of course, that can be hardwired in the computer to be instantaneous. So that says, so far, what have we said? We're saying that the 64 by 64 Fourier matrix is really separate your vector into the even components and the odd components, then do a 32 size Fourier transform onto those separately, and then put the pieces together again. So the pieces, putting them together, turns out to be I and a diagonal matrix and I and a minus that same diagonal matrix. So the fix-up cost is really the cost of multiplying by D, this diagonal matrix, because there's essentially no cost in the I part or in the permutation part. So really, it's the fix-up cost is essentially, because D is diagonal, is 32 multiplications. There you're seeing, of course, we didn't check the formula, or we didn't even say what D is yet, but I will. This diagonal matrix D is powers of W. 1 W squared down to W to the 31st. So you see that to do a multiplication by D, I need to do 32 multiplications. There they are. Then, but the more serious work is to do the F32 twice separately on the even numbered and odd numbered components. So twice 32 squared. So 64 squared is gone now. And that's the new count. Okay, great. But what next? So that's, we now have the key idea. We would have to check the algebra, but it's just checking a lot of sums that come out correctly. This is the right way to see the fast Fourier transform, or one right way to see it. Then you've got to see what's the next idea. The next idea is to break the 32s down. Break those 32s down. So we have this factor, and now we have the F32, but that breaks into some guy here, F16, F16. Each F32 is breaking into 2 copies of F16. And then we have a permutation, and then so this was a 64 size permutation. This is a 32 size permutation. I guess I've got it twice, because I'm just using the same idea recursively. Recursion is the key word. That on each of those F32, so here's 0, 0. It's just to get F32, this is the odd even permutations. So you see the combination of those permutations, what's it doing? This guy separates into evens and odds. And then this guy separates the evens into the numbers that the even evens, which means 0, 4, 8, 16. And even odds, which means 2, 6, 10, 14. And then odd evens and odd odds. You see, together these permutations then break our vector down into x, even, and 3 other pieces. Those are the 4 pieces that separately get multiplied by F16, separately fixed up by these i's and d's and i's and minus d's. So this count is now reduced. This count is now, what's it reduced to? So that's going to be gone. Because 32 squared, that's the change I'm making, right? The 32 squared, so it's this that's now reduced. So I still have 2 times it, but now what's 32 squared? It's gone in favor of 2 16 squareds, plus 16. That was, and then the original 32 to fix. Maybe you see what's happening even easier than this formula is. When I do the recursion more and more times, I get simpler and simpler factors in the middle. Eventually, I'll be down to 2-point or 1-point Fourier transforms. But I get more and more factors piling up on the right and left. On the right, I'm just getting permutation matrices. On the left, I'm getting these guys, these I's and D's. So that there was a 32 there, and each one of these is costing 32. Each one of those is costing 32. And how many will there be? So you see the 32 for this original fix-up, because D had 32 numbers. 32 for this next fix-up, because D is 16 and 16 more. I keep going. So the count in the middle goes down to zip, but these fix-up counts are all that I'm left with. And how many factors, how many fix-ups have I got? Log n. From 64, 1 step to 32, 1 step to 16, 1 step to 8, 4, 2, and 1. 6 steps. So I have 6 fix-up factors. Finally, I get to 6 times the 32. That's my final count. Instead of 64 squared, this is log to the base 2 of 64 times 64. Actually, half of 64. So actually, the final count is n log to the base 2 of n. That's the 32, a half. So can I put a box around that wonderful, extremely important and satisfying conclusion that the fast Fourier transform multiplies by an n by n matrix, but it does it not in n squared steps, but in 1/2 n log n steps. And if we just complete by doing a count, let's suppose a typical case would be 2 to the 10th. Now, n squared is bigger than 1,000,000. So it's 1,024 times 1,024. But what is n? What is 1/2? What is the new count done the right way? It's n, the 1,024, times 1/2, and what's the logarithm? It's 10. So times 10 over 2. So it's 5 times 1,024, where this one was 1,024 times 1,024. We've reduced the calculation by a factor of 200 just by factoring the matrix properly. This was 1,000 times n. We're now down to 5 times n. So we can do 200 Fourier transforms, where before we could do 1. And in real scientific calculations where Fourier transforms are happening all the time, we're saving a factor of 200 in one of the major steps of modern scientific computing. So that's the idea of the fast Fourier transform, and you see the whole thing hinged on being a special matrix with orthonormal columns. Okay, that's actually it for complex numbers. I'm back next time really to real numbers, eigenvalues and eigenvectors, and the key idea of positive definite matrices is going to show up. What's a positive definite matrix? And it's terrific that this course is going to reach positive definiteness, because those are the matrices that you see the most in applications. Okay, see you next time. Thanks.